Hi, good day dear audience. Today we are going to discuss how to solve such an integration. An integration made of two index functions in the numerator and the denominator having the same order fraction of two index functions. Why is it unique? Because the index of the numerator is equal to the index of the denominator, which is not the case in most partial fraction analysis, meaning when analyzing such a fraction into simpler fractions of lesser degree. Usually partial fractions have an index function in the numerator and an index function in the denominator, where p of the numerator is prime with respect to q in the denominator. Prime meaning lesser in order. Here the highest power in the denominator is n to the power n minus k, while in the denominator the highest power is to the power n. But in solving, not solving as an integration, analyzing such fraction into simpler fractions having the denominator of the first order and the numerator of zero order, there is no x to the power 0. We would have analyzing n fractions having the denominator power of the order n, and we would have n constant a1 a2 till a to the power n in the numerator and n constants together with x in the denominators. These are usually factors when analyzing the denominator function. And as you see here, solving, we took the LCM, that is nearly returned the denominator to its original form, ax plus b multiplied by x times 2 and cx multiplied by x plus 1. And on multiplying these two brackets and multiplying cx by the other bracket, we would obtain a number of terms in the numerator. When equate, we can solve our equations and find our constants a, b, and c, the coefficients of the same power of x. A and c equal to plus c equal to 3, and 2a plus b plus c is equal 0. There is no here. And b, the coefficient of x to the power 0, which is 5, because 5 is 5 times x to the power 0, which is 1. Grouping constants here, as you see, this is our integration after taking the LCM, ax squared plus 2ax plus bx plus 2b plus cx squared plus cx. And this is equivalent to the numerator of our fraction of equal x, having equal x index, a plus c times x squared, 2a plus b plus c times x plus 2b. That's the constant term. And we'll have 3 equations, as I said before, not 4. So, as I said, math have remorse on its users not to make him face more unknowns than the number of equations to be able to solve. Okay. And 2a plus b plus c is equal to 0 because we have here no coefficient, no term in x. And the third equation would be a plus c equal 3. So let us now solve these 3 equations. So here are our 3 equations. A plus c equals 3, and 2b is equivalent to 5, the constant term, and 2a plus b plus c equals 0. If you compare it here, the coefficients of x, a and c, the coefficient of x squared, a and c, the coefficients of x is 2a, and b and c, the constant term is 2b. It's okay. As I said, from 1 we have that c equals 3 minus a, and substituting from that into 3 we have 2a plus b plus 3 minus a. Okay. And then we all know that 2b equals 5, then this means that b equals 2.5, and resubstitute once more. And now substituting for b, which we said 2.5, because 2b is equal to the constant term equals 5, so b would be 2.5 is 2a plus 2.5 plus 3 minus a, which gives us a plus 5.5 equals 0, because 2a minus a, that makes 1a. So here would have a would be equal to minus 5.5, and we'll write it to remember it. Thus a here would be equal to minus 5.5. So here we got a equals minus 5.5, and substituting in a plus c, which is the coefficient of the x square, a plus c equals 3. So we have minus 5.5 plus c equals 3. And thus c would be equal, transferring the minus 5.5 to the right hand side, we get c equals 8.5. Now we have obtained the three constants, c 8.5, a minus 5.5, and b 2.5, and we can set out to perform the integration now. So this is our proposed form of integration, where we divided the original integration into these two simpler integrations according to the rules of partial fractions, and we will set out to substitute for the values obtained for a, b, and c and start performing our integration. And here is, as you see, our two integrations after substituting in the values obtained for the constants. And here, as you see, this integration yielded two integrations, 5.5x over x plus 1 and 2.5 over x plus 1 dx. Now these two integrations are simply would be ln integration, ln x 2.5 ln x plus 1 and 8.5 ln x plus 2. But what would we do with this integration? I explained it before in one of my videos, and I will repeat it here also. So here it is, the next step of our three integrations, 1, 2, and 3. So I solved the second and the third, 2.5 ln x plus 1 plus 8.5 ln x plus 2, but I left this to solve it alone. Now we'll see how it is solved. So here we'll put x plus 1 equals t, and thus x would be equal to t minus 1. And thus our integration now becomes minus 5.5 into t minus 1 over t dt. Taking the constant term outside the integration, 5.5 times integral t minus 1 over t dt equals minus 5.5 integral 1 minus 1 over t dt. So it is as you see here, which is equal to minus 5.5 t, because this is 1, it's the integral of 1 dt equals t minus 5.5 minus and minus, that makes plus, plus 5.5 ln t. Integral of 1 over t dt is ln t. But we should remember that we were given the problem in terms of x and not, so we should return it to its original quantities. Thus transforming what we've got here in terms of t to in terms of x, we get minus 5.5 into x plus 1 plus 5.5 ln x plus 1, and adding this to the integration of the other two fractions, we get this is the total integration here before integrating this term and dividing it into two integration, and this is the integration of the two rightmost terms and adding 1 to 2, which is the result of the integration of the leftmost partial fraction. We get, this is the integration of our problem, 5.5 x plus 1 plus 5.5 ln x plus 1 plus 2.5 ln x plus 1 plus 8.5 ln x plus 2. That's all, dear audience. I hope I have explained well and the problem was useful and interesting. Goodbye, good day, my dear audience.